So let's talk about the unit circle some more. So I know yesterday we kind of started to get into it, but here's the idea. So unit circle, circle of radius 1. We can draw any kind of radius we want from the center to a point in the circle. And I want to point out, again, also, I should actually say this class is called Trig Graphs and Trig Identities. And really entertaining trig graphs, at least not what I think it was trig graphs. I suppose you could say this is a trig graph because it's a graph that helps with trig. But when people say trig graphs, they usually mean like the graph of the sine function or the graph of the cosine function, which we'll get into in a couple of classes after the midterm, but it's not what this is. So I feel like this one's a little mislabeled. Don't worry about it. So we're going to write down the trig functions using this triangle and the fact that if this is the point x, y, that means we've gone over x. So the base of this triangle is x, and we've gone up y. So the height of this triangle is y. So there's a lot of things we can say here. But I want to talk about the trig function specifically. So sine, cosine, and tangent. We know that sine of theta is equal to the opposite over the adjacent, which you could write as y over r. But we know that r is 1, so that's really just y over 1, which is just y. Cosine of theta is x over 1, which is just x. And tangent of theta is opposite over adjacent, which is y over x. I'm going to label these, but I feel like these labels are kind of in the way. So I have labeled some points as well, because these are usual points, right? The point to the right is 1, 0, up is 0, 1, over is negative 1, 0, down is 0, negative 1. And then the angles, this is angle 0, pi over 2, pi, 2 pi over 2, and then all the way around is 2 pi. So this is how we typically think of the trig functions on the unit circle. And so what's interesting here is that you can think of this point, if you've gone an angle from the positive x-axis, an angle of theta, this point, I know we said this yesterday, I'm going to say it again, is literally the x-coordinate is cosine of theta, and the y-coordinate is sine of theta. And so often, when we're talking about angles that are larger than 90 degrees, or pi over 2 radians, we use this idea to be like, oh yeah, the angle is just the x-coordinate, or the trig function is whatever the trig function is, depending on if it's sine or cosine or tangent, right? Sine is y, cosine is x, tangent is y over x. And also we have the reciprocal functions. So that means cosecant of theta, which is 1 over sine by the reciprocal sign. Cosecant is just going to be 1 over y. And secant of theta is going to be the reciprocal of cosine, which is going to be 1 over x. And cotangent of theta is going to be the reciprocal of tangent, which is going to be x over y. A couple other things to say. There are two trigonometric identities that become really, really obvious when you write things this way. The first is that tangent, being y over x, is equal to sine of theta over cosine theta. So one trig identity, an identity just means it's true no matter what value your angle is that tangent of theta is equal to sine of theta over cosine of theta. This is really itchy all of a sudden. Okay. Another identity over here is that cotangent of theta is equal to x over y, which is cosine of theta over sine of theta. These are very commonly used trigonometric identities. When we're trying to kind of simplify a trig expression, which we'll be doing later in class today, often this is our go-to kind of thing. We're like, oh, I'm going to write things in terms of sine and cosine. Also, not that we don't already know them, but we know that cosecant of theta is 1 divided by sine of theta. We know that secant of theta is 1 divided by cosine of theta. So every trigonometric function, sine, cosine, tangent, cosecant, secant, cotangent, every trigonometric function can be written as some sort of combination of sines and cosines. And yeah, that's exactly right, Mason. Yeah, my cotangent does not look great, but let me write that again. That is cotangent, COT of theta equals cosine of theta over sine of theta. Oh, itchy nose. Sorry, my nose is really itchy. I don't know why. Okay. So look at that. Planned ahead. So this tells us, so far, here's our unit circle again, with the same usual special angles. So remind you, we've got 0 radians, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, pi, 7 pi over 6, 5 pi over 4, 4 pi over 3, 3 pi over 2, 5 pi over 3, 7 pi over 4, 11 pi over 6, and all the way around to 2 pi. I would strongly recommend everybody either look at the notes. You can look at the notes for class V and it's all written on there, or you could pull up a unit circle. In fact, now that I've got it in mind, I'm just Googling a unit circle, images. Let me grab one here. Sure, that's a great one. Can I put that in the chat? Maybe. Let's find out. No, I cannot. It just is that. Can you get it? No, I don't think so. I'm not that smart. Let me. So anyway, can I go to it? Sure. Here's the Wikipedia. Yeah, exactly. It didn't work. If you click on this link, I'm about to put in the chat. Here's the link. There's a link, and if you scroll down a little bit, you will see a picture with reds and blues of the unit circle. And if you click on it, you can get something like this. So this is what I am looking at, which is essentially the same picture I've got here, right? I've got all the angles, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, pi, 7 pi over 6, 5 pi over 4, 4 pi over 3, 3 pi over 2, 5 pi over 3, 7 pi over 4, 11 pi over 6. And yeah, this is a good picture, I think, that we're looking at. And importantly, it's got all these values, right? So these literally, these points here are the coordinates on the circle. They're also the values of cosine and sine, respectively. I'm going to stop sharing so I can point at my board, right? So for the angle pi over 6, cosine of pi over 6 is the square root of 3 over 2. Sine of pi over 6 is 1/2. For the angle pi over 4, cosine of pi over 4 is the square root of 2 over 2. Sine of pi over 4 is the same, it's the square root of 2 over 2. For pi over 3, cosine of pi over 3 is 1/2. Sine of pi over 3 is root 3 over 2. So I feel like this picture emphasizes what we were saying yesterday, which is that for angles that are larger than 90 degrees, or pi over 2 radians, you can find the cosine or sine, or really any trig function of the value, by using reference angles. So for example, 5 pi over 6. If I want to find cosine of 5 pi over 6, which I don't really have enough room to write, I guess I'm kind of make it fit over here. So I want to find cosine of 5 pi over 6. One option, and it's a valid option, is just to memorize it. You could totally, if you want to, memorize this entire unit circle. I don't recommend it. It's not how my brain works mathematically, but if that's what works best for you, do it. But I am going to say, you really, really, really need to be able to find sine, cosine, and the rest for any angle in this circle, because it's going to come up in future classes for sure, without a doubt, 100%. You're going to have to be able to find cosecant of 4 pi over 3 someday, or secant of 11 pi over 6, or cotangent of 7 pi, right? These are going to come up. You have to be able to find them without spending too much time just trying to figure it out. So one thing you do, you can totally memorize this. The thing I recommend is more memorizing the first quadrant and then using reference angles. So cosine of 5 pi over 6, well, I know the reference angle is pi over 6. And I know that cosine of pi over 6 is the x coordinate of pi over 6, which is root 3 over 2. And look, for 5 pi over 6, the x coordinate is the same, if you can see it, but it's negative, which makes sense because in the second quadrant where sine is positive, the other two cosine and tangent are negative. So if cosine of if cosine of pi over 6 is the square root of 3 over 2, cosine of 5 pi over 6 is the negative square root of 3 over 2. And that's kind of the whole idea, right? If I wanted to find, I don't know, sine of 4 pi over 3, I know that sine of pi over 3, I picked kind of the same thing, right, is the square root of 3 over 2. And I know that sine of 4 pi over 3, well, for 4 pi over 3, the reference angle is pi over 3. That's why I'm looking at pi over 3. I know that sine of 4 pi over 3, since we're in quadrant 3 for 4 pi over 3, that's equal to negative root 3 over 2. That's kind of the whole idea. Again, I know I said that already, but that's most of the idea, is to find sine or cosine or tangent or secant or cosecant or cotangent of an angle. You find the reference angle, you see what sine or cosine or whatever is of that angle, and then you find the appropriate positive or negative for the angle you're actually looking at. So one more example, over here. Let's say I wanted to find, I don't know, I want to find cotangent of, let's do 7 pi over 4. Okay, 7 pi over 4 is a pi over 4, right? The reference angle is pi over 4. The reference angle is pi over 4. And I know that cotangent of pi over 4, well, you could do it any number of ways. I usually don't remember what cotangent actually is. You could say either cotangent is x over y if you really wanted to, or I would probably think of it as cotangent is cosine over sine. Cotangent of pi over 4, well, cosine of pi over 4 is root 2 over 2, and sine of pi over 4 is also root 2 over 2. The thing I remember about pi over 4 is cosine and sine are the same. So the cotangent and tangent are both equal to 1. So cotangent of pi over 4 is 1. 7 pi over 4 is not pi over 4, not 3 pi over 4, not 5 pi over 4, but 7 pi over 4 is in quadrant 4, where cosine is positive. The other two, sine and tangent, are negative. If tangent is negative, its reciprocal cotangent is also negative. So cotangent of 7 pi over 4 is negative 1.
I have a question.
Go ahead.
What if we want to find one that's not on the unit circle?
Every angle's on the unit circle.
Well, like, what if we did, like, I don't know, like sine of 7 pi over 5 or something?
Okay, so you mean a not special angle?
Yeah, like finding the reference angle of something like that where we can't use the unit circle.
Sure. Well, you can still, it still is on the unit circle, but it's not going to have a value that we're aware of. So the answer to your question really is that we, at that point, we use a calculator. So what I'll say is these are the angles that you need to be able to evaluate without using a calculator, because someone's going to expect you to do it on the test someday when you're not using a calculator. I can't say there's another good reason for it other than they come up often enough that you don't want to have to be reaching for a calculator every time you're trying to evaluate it. I know that's somewhat unrealistic these days because calculators are easily available. There are markets, right? But someone's going to give you a test someday where like find sine of 2 pi over 3 and you can't use a calculator because I hate you. So, but you're right. For other angles like 7 pi over 5 or 9 pi over 17 or anything where the denominator isn't 2 or 3 or 4 or 6, then yes, we use a calculator because that's what we do. Yeah. Good question. Not a good answer, but it's the truth. But for these angles, we want to be able to use the unit circle to evaluate them. Let me grab this. And again, I will say there are multiple ways of imagining this. You can either do what I do, which is I do really remember the angle values in the first quadrant. Right? I know without looking at this that sine of pi over 6 is 1/2, and sine of pi over 4 is root 3 over 2, and sine of pi over 3 is root 3 over 2. In fact, there's a nice pattern for sine and cosine in the first quadrant, which I'll talk about maybe in a minute. Yeah. Do I want to talk about it now? Yeah, I kind of do. So let's look at this for 1 second. I'm going to write some things down here. Yeah. So there is a nice pattern for sine and for cosine in quadrant 1. So the other thing I want to say, which is what we're leading towards, is that this unit circle allows you to find sine and cosine and other trig functions for angles that you don't get in a triangle at all, like 0 degrees, right? You don't have a triangle that has a 0 degree angle, or two 90-degree angles, right? You can't find sine of 90 by using a right triangle, because if, right, you can't be like, okay, well, there's my 90-degree angle, and if you write opposite over hypotenuse, that doesn't work. So what the unit circle does allow for specifically is to find trig functions of what are called quadrantal angles, meaning angles that aren't in any quadrant, like 0 radians, or pi over 2 radians, or pi radians, or 3 pi over 2 radians, or 2 pi radians. Basically, any angle that ends up on an axis is called a quadrantal angle. I love saying the word quadrantal, it's a great word. But a quadrantal angle isn't in a quadrant, right? 90 degrees isn't in quadrant 1 or quadrant 2. It's between them. Pi radians isn't in quadrant 2 or quadrant 3. It's between them. So that's what this will do. So what we can see here is that, oh, cosine of 0 radians is 1 because it's the x value. Sine of 0 radians is 0 because it's the y value. Cosine of pi over 2 radians, like this is pi over 2 radians, is 0. Sine of pi over 2 radians is 1. So this unit circle allows us to know what sine and cosine are for angles that are not angles you could find in a triangle. So now I want to make a little table, because, and again, this is kind of a quick aside here, but what I want to tell you all is that we can find sine and cosine for these first 5 important values. I'm going to write them very, very specifically. So here are the first 5 important angles. So the angles are 0 radians. I'm going to write them in increasing order. Pi over 6, pi over 4, pi over 3, and pi over 2. Which I'm sure we can also say as 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees. Now we're going to write down the sine values. And I'm going to write them in a very kind of special way in a minute. So sine of 0 radians, which is the same as 0 degrees, is 0. Sine of pi over 6 is 1/2. Sine of pi over 4 is the square root of 2 over 2. Sine of pi over 3 is the square root of 3 over 2. And sine of pi over 2 is 1. Something to think about is that in the first quadrant, as the angle gets larger, the sine value gets larger, which makes sense because in the first quadrant, the sine value is the y coordinate. And as you go from here to here, the y value is always getting bigger. So in the first quadrant, bigger angles mean bigger sine values. It also means bigger angles mean smaller cosine values, because cosine is the x coordinate, which starts out being 1 and gets smaller and smaller and smaller and smaller and smaller until you get to 0. So in the first quadrant, a bigger angle means a smaller cosine value. Okay, here, yeah, I'll write that first. I'm gonna leave myself some room here. Here's cosine. In fact, the cosine values exactly are the mirror image of the sine values. Cosine starts at 1 and then gets smaller, and then gets smaller, and then gets smaller, and then gets smaller. Now there's a super duper cool pattern that a student showed me one time, which is the following. You can write all of these as the square root of a number over 2. This is the square root of 0 over 2. This is the square root of 1 over 2. This is the square root of 2 over 2, right? It didn't change. None of these change. We're just writing them differently. This is the square root of 3 over 2. I'm not writing it differently. And what would you love for the pattern to give us? If it's square root of 0, square root of 1, square root of 2, square root of 3, we would like this to be the square root of, what comes after 3? And it is. Square root of 4 is 2. 2 over 2 is 1. So this kind of cool pattern where you can say, oh, if the whatever angle you're at in the first quadrant, sine is just whichever, like, so if you're at the first, second, third, fourth, or fifth, or I should say maybe the 0th, the first, the second, third, and the fourth, sine of the angle is the square root of that number. So there's like this trick where you use your fingers, and you're like, okay, if I'm at the, I don't know, the fourth angle, I go 1, 2, 3, 4, and cosine is the square root of 3 over 2. Cosine is the square root of 1 over 2. Totally works. That's right. So you kind of, you start here and you go, okay, 1, 2, 3, 4, right? Put down your fourth finger, sine is root 3, cosine is root 1 over 2. Kind of a neat pattern. And cosine is the reverse, right? This is the square root of 4 divided by 2. These don't change. This is the square root of 1 divided by 2. Square root of 2. Okay, so when I'm kind of circling around a lot, maybe not saying super explicitly, so I'm going to try and make sure I say it. You need to be able to evaluate these trig functions. You have to be able to find sine of anything and cosine of anything, tangent of anything. But once you can find sine and cosine, you can find tangent. So the nice thing about tangent of any of these values is that tangent is just sine divided by cosine. So tangent of 0 is 0 divided by 1, which is 0. Tangent of pi over 6 is 1/2 divided by root 3 over 2. Now the nice thing about this is when you have fractions divided together, if they have the same denominator, they cancel. Right? This is really 1/2 times 2 over root 3. The 2's cancel, you get 1 over root 3, which we usually rationalize as root 3 over 3. Tangent of pi over 4 is going to be this over this. Well, when you have something divided by itself, square root of 2 over 2 divided by square root of 2 over 2 is 1. This one is the square root of 3 over 2 divided by 1 over 2. Again, you multiply. That's the square root of 3 over 2 times 2 over 1. The 2's cancel, and you get the square root of 3 over 1, which is just the square root of 3. Finally, this last one, tangent of 90 degrees or pi over 2 radians, is 1 over 0, which is undefined. So for some of the trig functions, tangent, cotangent, secant, and cosecant, there are going to be some values, some angles where they are not defined, where you get division by 0. Another way of saying that would be that the angle pi over 2 radians is not in the domain of the tangent function, because tangent of pi over 2 is undefined because we get division by 0. So what this section, I'm going to erase my picture. I didn't make it take that long, but I did spend some time. Yeah, I guess I'm going to erase my picture. Because really so I'm never actually drawing out that whole picture. The picture I'm really drawing out is sometimes my abbreviated unit circle. Specifically, if I'm being asked to find trig functions of quadrantal angles. So if I was being asked to find, like, I don't know, sine of pi and cosine of pi and tangent of pi, here's the unit circle I would actually draw. I would draw the unit circle with these 4 points. I often call it the 4 corners of the unit circle. I know a circle doesn't have corners, but it's easier than saying the 4 cardinal directions of the unit circle. So this point is 1, 0. This point is 0, 1. This point is negative 1, 0. This point is 0, negative 1. And I know this angle is 0 or 2 pi if we go all the way around. This angle is pi over 2. This angle is pi. This angle down here is 3 pi over 2. So we've got the whole kind of picture. And then we're looking at pi. So sine of pi is the y coordinate, which is 0. Cosine of pi is the x coordinate, which is negative 1. Tangent of pi is sine divided by cosine, which is 0 divided by negative 1. 0 divided by not 0 is just 0. I guess we might as well find the other 3. Let's do the reciprocals. cosecant of pi, secant of pi, and cotangent of pi. So cosecant of pi is the reciprocal of sine. What's the reciprocal of 0?
Would it be 0?
It's not 0. What do we do? What's happening here? We are dividing by 0, which is, what's 1 divided by 0? How many times does 0 go into 1?
0.
6 times? 6 times 0 is 0. 1 minus 0 is 1. Oh, I could have picked a bigger number.
Would it be undefined?
Right. Right. So what I'm trying to point out here is that when you divide a number by 0, it can go in any number of times you want. You picked 100. I picked 1,000,000. Someone else picked 1,000,000,000. 1 divided by 0 is undefined. What's happening there is you're getting something that's getting infinitely large, because 0 can go into 1 an infinite number of times and you still aren't done. Secant of pi is the reciprocal of cosine of pi. So it's 1 divided by -1, which is -1. And cotangent of pi you can either think of as cosine over sine, which is -1 over 0, or you can just think of it as the reciprocal of tangent, which is -1 over 0. Again, we're dividing by 0, which means what?
It's undefined.
Right. I really want to make that stick in your guys' heads, because I've seen many, many students over the years often say that division by 0 equals 0, and that's not true. Division by 0 is always undefined. Sometimes it's undefined in a very specific way, which we'll learn more about in calculus, but it's undefined. What I also want to mention, for any quadrantal angle, meaning any angle that ends on one of the x or y axes, you're always going to have this pattern where of the 6 trigonometric functions, 2 of them are 0. 2 of them are undefined, because if 2 of them are 0, their reciprocals have to be undefined. And 2 of them are either negative, both -1 or both +1. It's always going to be true for a quadrantal angle. 2 zeros, 2 undefined, and 2 1s or -1s. Not a 1 and a -1. You either get 2 1s or 2 -1s. Let's look at another example. Let's look at, say, let's look at 5 pi over 2. So I want to find the 6 trig functions for 5 pi over 2. 5 pi over 2, that's not on my list. So 5 pi over 2 is more than 1 full revolution. Right? 5 pi over 2 is 4 pi over 2 plus pi over 2. 4 pi over 2 is 1 full revolution, and then another pi over 2, put this right there. So 5 pi over 2 and pi over 2 are called coterminal angles, meaning they end at the same place even though they don't have the same value, right? 5 pi over 2 is something like, I don't know, 7.5 or 8. Pi over 2 is like 1.5, 1.57 or something. But they still have the same trig functions for the angle. So sine of 5 pi over 2 is the same as sine of pi over 2, which is going to be +1. Cosine of 5 pi over 2 is going to be 0, right? Sine is the y coordinate, cosine is the x coordinate. If you ever are not sure, just remember they're alphabetical. X comes before y, cosine comes before sine. Tangent of 5 pi over 2, 1 divided by 0 is undefined. It's okay if you write equals undefined, but technically it's not really the right thing to do. So I just really like to write tangent of 5 pi over 2 undefined, not equals undefined. But if you write equals, it'll be okay. But try not to. Cosecant of 5 pi over 2 is the reciprocal of sine, which is 1 over 1, which is 1. Secant of 5 pi over 2 is 1 over 0, which is undefined. And cotangent of 5 pi over 2, well, you could say it's the reciprocal of tangent, but that's not super helpful because the reciprocal of undefined, is usually 0, but it's kind of weird to say it that way. We should really do that. Oh, cotangent is cosine divided by sine, which is 0 divided by 1, which is 0. So look, same pattern. 2 zeros, 2 undefines, 2 ones. It's always going to be the case. Sure. So if I said something like, so let's just make it a little bit easier for a second. What if I wanted to find secant of 17 pi? Well, it's definitely more than one full revolution. How many full revolutions is 17 pi?
Would it be like 8.5 or something like that?
Exactly. It's exactly 8.5 revolutions because one revolution is 2 pi. So multiply both sides by 8, and 8 revolutions is 8 times 2, 16 pi. So basically, a multiple of pi is either going to be a full revolution or a full revolution in another half. And it's a full revolution if it's an even multiple. It's a full and then another half if it's an odd multiple. So, right, 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, 12 pi, 14 pi, 16 pi, and then half a revolution to get to 17 pi. You don't need to draw that. I'm just trying to show you. Right, so odd multiple of pi is going to get you to this point over here. I know that at this point over here, the point on the unit circle is -1, 0. I know that cosine is equal to -1. I should say cosine of 17 pi is equal to -1. So secant of 17 pi is the reciprocal of that, which is also going to be -1. So whenever you've got an angle that's bigger than 2 pi, you just kind of think about how many revolutions do I have and then what's left over. The same is true if I wanted to find something like, I don't know, sine of, sorry, now I'm like, sure, brain work. Sorry, my brain stopped working. 61 pi over 6. Yeah, I know. So 61 pi over 6, I can break that up as 60 pi over 6 plus 1 pi over 6. 60 pi over 6 is 10 pi, which is 5 full revolutions. So this angle is going to be the same as going around 1, 2, 3, 4, 5 times, and then pi over 6. So pi over 6 and 61 pi over 6 are coterminal. They end at the same terminal ray. So this is literally equal to sine of pi over 6. Right? They both have the same reference angle and the same quadrant. And sine of pi over 6 is the small angle, which means sine is the smaller value, which is 1/2. Sine of pi over 3 is the larger value, which is √2. Okay. So now let's talk about some identities. Again, a trigonometric identity is just a thing that is always true for any value where the trig function is defined. So, and I know I already mentioned this one, but let me say it again. So these are often called the quotient identities. The tangent of theta is equal to sine of theta over cosine of theta. And cotangent of theta equals cosine theta over sine theta. These are some of the most frequently used trigonometric identities that we have. We also have some Pythagorean identities. meaning they literally come from the Pythagorean theorem. So remember in our picture of our unit circle, there's our angle theta. I'm not picking any particular angle, it's just our angle theta. And we have this triangle where this side is x, and this side is y, and this side is 1, because it's a unit circle. We know for this unit circle that, how do I want to write this? I'm going to write it kind of atypically, but we know that x squared plus y squared equals 1 squared. Or I'm going to write y squared plus x squared equals 1. 1 squared is 1. But then we also know that x is cosine theta and y is sine theta. So we can replace y with sine and write sine theta squared, or the abbreviated way, sine squared theta plus cosine squared theta equals 1. We also know that this equation is true because it's the equation of a circle of radius 1 third of the origin, right? X squared plus y squared equals 1 is this circle here, coming from the Pythagorean theorem. There are other ways of writing this. Sometimes we like to isolate either sine squared or cosine squared. So alternative versions are sine squared theta equals 1 minus cosine squared theta, or cosine squared theta equals 1 minus sine squared theta. We can check this, meaning we can verify this identity for a particular value. So what I want to say is this identity is always true, no matter what angle you pick. We can pick a couple angles and show it's true for those angles. So for example, we can verify that this identity is true for, I don't know, let's say our angle is 4 pi over 3. So my reference angle is pi over 3. I'm in quadrant 2. So I know that sine is positive and cosine is negative. I know that sine of 4 pi over 3 is, it's a pi over 3, and the sine of pi over 3 is root 3 over 2. So sine of 4 pi over 3 is also positive root 3 over 2. Cosine of 4 pi over 3, on the other hand, is going to be negative, and it's going to be negative 1/2. How do I know it's negative 1/2? Well, here's what I know. When you've got a pi over 3 or a pi over 6, you know, if I should say, if your reference angle is pi over 3 or pi over 6, you're in a 30, 60, 90 triangle. And one of your sine or cosines will be 1/2, and the other one will be root 3 over 2. Right? If you're in a 30, 60, 90 triangle, it doesn't matter if this is your angle or this is your angle. One of them is going to be root 3 over 2. One's going to be 1 over 2. If it's this angle, cosine is 1/2, sine is root 3 over 2. If it's this angle, sine is 1/2, and cosine is root 3 over 2. What I'm really trying to say is that if you have one of those angles, something pi over 3 or something pi over 6, you always get these two values for sine and cosine. One of them is a root 3 over 2, positive or negative. One of them is a 1/2, positive or negative. They always go together. So then let's verify that this is true. So sine squared of 4 pi over 3 plus cosine squared of 4 pi over 3. I'm not going to say it's equal to 1. I'm trying to show it's equal to 1. So I'm going to say it's equal to, well, sine of 4 pi over 3 is root 3 over 2. So sine squared is root 3 over 2 quantity squared. Cosine squared, well, that's going to be negative 1/2 quantity squared. Square root of 3 over 2 squared is just the square root of 3 squared, which is 3, over 2 squared, which is 4, plus a negative number squared is going to be positive. It's going to be positive 1 over 4. 3/4 plus 1/4 is 4/4, which is 1. So it works.
Can you?
It would work
sorry.
for any of the angle bit. Go ahead.
I wanted to ask, can you explain one more time how we got the RA and determine the quadrant?
Sure. So the reference angle for one of our special angles, the reference angle is always just, if it's written in radians, it's just pi over whatever the denominator is. You could also change this to degrees, right? In degrees, this is going to be times 180 over pi, which is going to be 240 degrees. Oh, you know what? I might have made a mistake. That's the issue here. Is that I did make an error. I for some reason I saw that as 2 pi over 3. I apologize. 4 pi over 3 is not in quadrant 2. It still has the right reference angle, pi over 3. We're actually in quadrant 3. I am sorry. Good call. Yeah, I should have used my tried and true method of saying. So what I thought I was doing, I was making a mistake, was I know that pi over 3 is the first pi over 3. It's in quadrant 1. I know the next one that doesn't reduce is 2 pi over 3 in quadrant 2. I know the next one that doesn't reduce. So 3 pi over 3, that reduces, right? That's pi. That's a quadrantal angle. But then 4 pi over 3 is in quadrant 3. So yeah, I'm in quadrant 3 here, not quadrant 2, which means cosine is negative 1/2, and sine should be negative root 3 over 2, which means this should be negative root 3 over 2. It's not going to affect our final answer because a negative root 3 over 2 squared is still going to be a positive 3/4, but we should be writing the right thing. So again, thanks for the catch. I apologize for the mistake.
No problem.
Now I feel like I should do another one, but I should also do that. Okay. So let's talk about trig identities for a minute. Or using trig, I should say, using trig identities to simplify expressions. So I want to simplify the following to a single trigonometric expression. I feel like there's one homework problem that says simplify to a single trig term, but it actually has a couple. I'll double check that just to be sure. So I want to simplify cosine of x times cotangent of x plus tangent of x. And this is supposed to simplify to a single term, meaning sine of x or cotangent of x or something. And my usual go-to first thing I'm going to do is to rewrite everything in terms of sines and cosines. That's not always the first move you want to make, but it is often the first move you want to make. So I'm going to write this as cosine of x times cotangent is cosine of x over sine of x plus tangent of x, which is sine of x over cosine of x. And you might have noticed I left a little extra space here because if I want to add these fractions, I need a common denominator. So cosine over sine and sine over cosine, the denominator is going to be sine times cosine. So I have to multiply this by cosine x over cosine x, and this by sine x over sine of x. So what do I get? I get still this cosine x out in front. I don't want to distribute this in. Cosine times cosine is cosine squared x. Sine times sine is sine squared x. And they do have the common denominator of sine x times cosine x. Well, look, now I can use the identity that cosine squared x plus sine squared x is equal to 1. So this can be rewritten as still cosine x times 1 over sine x times cosine x. At this stage, you could either cancel the cosine, or you could first write it as cosine x over sine x times cosine x. Then cancel the cosine, write it as 1 over sine of x, which then we could write as cosecant of x. So yeah, this expression simplified to one single trigonometric term. Let's do one more. We'll be pretty much out of time. Yeah. Yeah, I'll double check the V to make sure there isn't anything silly. Let's look at this next one here. Sine of x divided by secant x cosecant x minus cotangent x. Secant x times cosecant x minus cotangent x. Is that right? Yeah. A lot of these problems, the name of the game is write everything in terms of sines and cosines, common denominators if you need it, et cetera, et cetera. So I'm going to write this as sine of x divided by secant is 1 over cosine of x. Cosecant is 1 over sine of x. And cotangent is cosine of x over sine of x. All right. I've got two fractions. This fraction has a denominator of cosine x times sine x. This fraction has a denominator of just sine x. So I need a cosine times a cosine. Sorry, a cosine over cosine. I need a cosine x over cosine x. So that this fraction and this fraction have the same denominator. So what have I got? I've got sine of x divided by one big fraction. The fraction in the denominator is going to be having its own denominator of sine x times cosine x. And its numerator is 1 minus cosine squared. We know that 1 minus cosine squared x is equal to sine squared x. So this is equal to sine of x divided by sine squared x over sine x times cosine of x. You can cancel one of the signs. So cancel a sine here and a sine there. So now you've got sine x over sine x over cosine x. Although you could write that as sine over tangent, I don't really want to. What I want to do is I want to rewrite this as sine of x. Instead of dividing by this, I'm going to multiply by the reciprocal. These signs will cancel. If you don't like seeing that, write this as sine of x over 1. It's going to be a little easier to see they cancel. So these cancel, and you get cosine x.